in school? Does not have a really early morning class?
No, he left.
So this is one of those days that you look forward to. Oh, it's not hard. That's
I just use that.
oh.
I'm thinking about putting the word man, JC, and a I symbol. And this is actually showing our little.
Oh, that's true.
All right, well. Good morning. Well, it's time to begin, so let's go ahead and get started. Okay, today we're going to be working on inverse functions, chapter 4.1. Here are some of the skill sets that we're going to be doing. Okay, first we need to determine what is a one-to-one function. The function is called one-to-one if you've got two different x values, we'll call them A and B, that are part of the domain or the total set of x values. If A and B are different points on the x-axis, then the equation with A and the equation with B should have different values. However, if A and B are really the same point or have the same value, for example, 5, then A equals B. Well, that seems pretty obvious. Let's go on. Here we have a set of points, a set of domains with 2, 4, 7, and -2, a set of ranges with 1, 2, 3, and 1 again. Notice that in this case, we have the same y value for two different x values. That would be like the two legs of a quadrilateral. Okay, so we got different x's, but the same y's. Then that would not be one-to-one. Okay, it is a function, but it is not one-to-one. Okay, here's a Venn diagram item. Batman matches to Bane. Green Lantern matches to Sinestro. Wolverine matches to Juggernaut. Now, in this case, for every y, we'll call these y, we'll call this x, there is one and only one x. And for every x, there is one and only one y. So this is yet a one-to-one relationship. Now, we've got an equation. It says it is one-to-one if no horizontal line intersects the graph in more than one place. We call this the horizontal line test. I want you to remember the vertical line test we used earlier to determine if it was a function. Well, the horizontal line test determines whether it is one-to-one or not, or in other words, more specialized. The inverse. We get an inverse by interchanging the first and second coordinates of each ordered pair in a relation. Okay, in the case of an equation, if y equals x squared minus 2x, we replace all of the y's with x's, we replace all of the x's with y's. Okay, when we do that, then it's an inverse. Now, that will also produce a reflection across the diagonal y equals x line. In other words, 45 degrees through the origin. Okay, g of x, and I've got a little symbol right in front of me. Here I said, got a set of points. Okay, so here is the set of points, the original set of points, okay, in blue. Now, if we reverse the x's and y's, interchange them is the word, then we get this set of points here, okay? In other words, it just flips all of these across the x, or this diagonal line. And those are the inverses. And that'll be the case with everything, whether it's a quadratic or a cubic or whatever the shape might happen to be, okay? Okay, I've got a set of random points here. They want to determine if this satisfies the requirement for 1-to-1. So what we're going to do is we're going to use the horizontal line test. In this case, each horizontal line only passes through one point. So therefore, this passes as a 1-to-1 function, whatever would produce that set of points. Is this a 1-to-1? Well, no, because you're intersecting in multiple points. Okay, this is a cubic graph, a graph of a x cubed function. Okay, and it goes through the origin as you see. Well, is this one? If we draw our lines, it only strikes in one place. So this one is a 1-to-1 function. Okay, here's a set of rules. I'll let you read this. Okay, there are three main thoughts in this page. The first thought is, if it's 1-to-1, then both the inverse and the original function are functions. Here is the second thought. If you look at the domain of the function f, then the range of the inverse is the same as the domain of the original. Okay, and in this case, the domain of the inverse is the same as the range of the original. So in other words, the domain and the range just trade places. And then finally, if the graph goes upwards, increasing over its entire domain from left to right, or is going downwards over its entire domain from left to right, then it is a 1-to-1 function. However, if it turns and goes down a while and up a while, then that will not be the case. Here we have three graphs. Are they 1-to-1 functions? Well, in this case, here, the horizontal lines strike in more than one point, so the answer is no. This is the inverse of an absolute value function. Okay? Now, in this case, it only strikes one place. You would think this would be 1 to 1. However, on the original equation, the horizontal line would not work, but the vertical line would work. Okay, now the third one. This is our square root function. Okay, this is our square root function. Originally, it would start here at the origin and go up, but this one has been shifted left 4 places. We look at the horizontal line test, and it also is yes. That was my grandson's phone, or my wife's, somebody's. Okay, graphs of a relation and its inverse. Anything is a relation. Then you have specialized requirements for it to be a function, meaning the vertical line test. And now we have the inverses. So if a relation is given by an equation, then the solutions of the inverse can be found to those by interchanging the first and second coordinates, translated, interchanging x and y values for each ordered pair in their graphs. Thus, the graphs of a relation and its inverse are reflections of each other across the diagonal line y equals x. Okay, here I have this equation. I interchange the x's and the y's. Okay, you notice this would be the x column, this would be the y column, the x column, the y column. Notice these are all just reversed. Now, here are the graphs of these. The blue is the first graph. It's just a quadratic, okay? With the y-intercept is 0. This one, when we graph it, we pick values of y and solve for x. Well, look what happens to it. If you consider this line, then it is a perfect reflection across this line. This point is the opposite of that one, okay? And these 2 points happen to be the same point. But you notice right here, you have the point 0.5. And here you have the 0.50. So that shows how they reflect across the equation y equals x. Now, let's use this definition of 1 to 1 to determine if an equation is 1 to 1. Here's the original equation. We're going to do a substitution of A for the x over here on the left. We're going to do a substitution of B for the x over here on the right and see if they are equal, A, B, C. So we substitute here, we substitute there. We subtract 2 on both sides. We divide by 3 on both sides, and we get A equals B. So yes, it meets the 1 to 1 function rule. Okay, what about this one? Okay, again, we're substituting A and B. We're seeing if 3A squared equals 3B squared. Well, we square both sides. First, we divide both sides by 3. Then we have both sides squared. We take the square root of both sides, and we get A equals plus or minus B. Okay, using the property of square roots rule. So, because we potentially have an A equals negative B instead of just A equals B, then no, it is not 1 to 1. Now, I will tell you, all lines and their inverses are 1 to 1. Quadratics, No, not unless you take some special restrictions on it. Okay, let's continue with determining if two functions are inverses. Okay, here's the way you check it algebraically. Now, up to this point, we've looked at it graphically, and you can see if the point's reflected across that diagonal line. But in this case, we're not going to graph it, but we're going to check the equations algebraically. So we're going to use the compose function, f compose g. That means we're going to take the g equation, substitute it into the f equation's x values, and see what answer we get. Now, if we get 1x for both this way and the opposite way, if we get 1x both ways, then it is an inverse. So what that implies then also is if you take an equation and its inverse and you compose them, you will get 1x as the answer. Either way. Here are two functions. Now let's try in reality what that theory just tried to show us. Here's this one, here's this one. Okay. Now, we're going to take f and we're going to compose g. That means we're going to replace this x with 1/3 x minus 2. So here we go, the 3. We replace the x with g and plus 6. Okay, that simplifies a little. First thing we do is distribute, and 3 times 1/3 is 1, and 3 times -2 is -6, and then we got this plus 6 on the end. You simplify this, the 6's cancel out, and we get 1x. Okay, if we had not gotten 1x, then we would know automatically it's not 1-to-1, so we wouldn't have to do the other half of this compose. But since we did get 1x, we've got to go check it the other way as well. Here we had f compose g of x. Here we're going to compose g compose f of x. This time we're going to take 1/3. We're going to replace the x with 3x plus 6 minus 2. We simplify that. First we distribute the 1/3. Then we combine the 2's and we get 1x again. Since we got the same exact 1x both ways on this, then yes, these are 1-to-1 functions, and yes, they are inverses. Okay, determine if they're inverses. What are we going to do? We're going to compose this and that, both directions. Okay, the first one, f compose g. We take the f, and that's a 5 right there. Okay, I slid this up and tried to move some stuff around so the hot spot wouldn't show if I were in the classroom. I'm at home this morning. At any rate, we've got f is x plus 1, so we replace this x right here with 5x plus 1 over 5. Okay, there we go. And we got 1x. The other way, we still get not 1x. We get x plus 2. So what that says is these two equations are not inverses. Okay, I've got x plus 6 over 2, and I've got 2 times x minus 6. We need to test them. So first we're going to replace this x with 2 times x minus 6, the whole thing. Okay, and this is the other way of writing that. We're going to take the g equation and substitute it into the f equation's x values. Okay, here we go. 2 times x minus 6 plus 6 over 2. Okay, we distribute that. 2x minus 12 plus 6. We simplify it over 2. 2x minus 6. 2 goes into 2 once. 2 goes into 6 3 times. So we get x minus 3. Now, for these to be inverses, we had to get 1x. So since we got x minus 3, then it is not inverses. And you don't even need to check the other way if you get the front way or the first way something besides 1x. You don't even need to bother to check the second one. Okay, now let's do m and n. We're going to take this n equation and substitute it for that x in the denominator. This one's going to be a little bit nasty in terms of calculations. I'm going to go a little slower so you can write this down. Hopefully you can see it okay the way we're doing it, that it'll be large enough. So we've replaced this x with 2x plus 5 over x. Okay. Now, the next thing I did was this 2 out here, I multiplied by x over x. So I would have a common denominator in the denominator. That way I could take this 2x, that 5, and this minus 2x and combine them to get 5 over x. Then I'm going to take this 5, which is 5 over 1, and I'm going to multiply it by the reciprocal. Remember from grade school fractions, you take the divisor and the reciprocal of it and then multiply. So we get 5 times x over 5. The 5's cancel, and we get 1x. So far, so good. Now here's the calculations for doing n composed g, or m. Easy for me to say. So I've got 2 x's in n. So I have to replace the top x with 5 over x minus 2, and I have to replace the bottom x with 5 over x minus 2. Okay, I distribute this, I get 10 over x minus 2 plus 5 over 1. Here I get 5 over x minus 2. And we're going to go back and do that complex rational thing that we did back in chapter 1. You find the common denominator of all the terms, which is x minus 2, and you multiply that common denominator, you can see it here in green, times all terms. Then cancel where you can. Well, these two cancel. Those two cancel, leaving me 10 plus 5 times x minus 2 over 5. Well, 5 goes into 10 twice, 5 goes into 5 once. So all I've got then is x minus 2 there, 10 plus x minus 2. And of course, that's a 1 there. And you simplify this and you get 1x. So we have 1x here, 1x there. And that brings us to our conclusions. Since both m compose n and n compose m both equal x, then they are inverses. Now, what we've done up to this point is we've identified what constitutes one-to-one, and we found out whether something is an inverse or not. We can either look at it graphically and see if it reflects across the x-axis, the y equals x diagonal line, or we can do the composition both directions and see if we get 1x. Now we're going to actually find the inverse of just a function. Okay, here's your procedure. There are 4 steps. These are the 4 steps. I'd suggest you write them down. This is important. Step 1, we're just renaming f of x to y. I told you that the first week of class. Anytime you see f of x, you think y. The second step, we interchange the x's and y's. The third step, we simplify the equation and isolate the y. Then finally, the fourth step is we replace that y with the notation f inverse of x. When you see this, that's not a power. Excuse me. That's a notation that means the inverse function of f. So there are your 4 steps. Now, let's look at this problem. We'll look at it both graphically and we'll look at it algebraically. Okay, we've got this. The first thing we're going to do, we're going to replace f of x with y. Second thing, we're going to interchange the x's and the y's. Third step sometimes takes multiple steps to get that y by itself. And then finally, the last step is we exchange this y for this f inverse of x notation. Okay, here in blue is the equation given by this. In other words, your y-intercept is 2. We could have written this equation 1/2 x plus 2. It's a line. So the y-intercept is 2, and it goes up 1 over 2, up 1 over 2. Now, what about this one? Y equals 2x minus 4. Well, right here's minus 4, the y-intercept of this one, and it goes up 2 over 1, up 2 over 1. And there's the equation. Now, if you look, I'm holding the marker there now. This creates a reflection across that diagonal. Okay. Now you can see the reflection a little better. Okay, let's test this one. Now we're testing it algebraically. We did it graphically and it reflects. So yes, this thing ought to be. Okay, just because we found the inverse doesn't mean it's 1-to-1. What we're going to do now is we're going to algebraically test this to see if it's 1-to-1. Actually, the graphs show that it is also. because every value is reflected. So we test it. Here's F, here's F inverse. We compose those two. There should have been a parentheses X right here. I mean, a parentheses around that and an X. And we replace this X with that equation. And it simplifies and we get 1X. Okay, now we're going to take this equation and we're going to sub in that. We simplify it and we get 1X again. So that verifies, since we got 1X in both directions, that this thing is 1-to-1. That it tells us, one, they are vertexes, and it tells us that they are 1-to-1. Here's another one. F of X equals 4X plus 3. Now, I'm going to tell you right now a shortcut. This is the equation of a line. Because it's the equation of a line, when we find its inverse will be 1-to-1, okay? Because that's the case with all lines and their inverses. So anyway, the steps. The first step, X plus 3. Second, we exchange the F of X for Y. Second step, we interchange the X's and Y's. We simplify it, so we get Y equals X minus 3 over 4. And then we put, and I left it out, and I'd better put that in now. Okay. So we put back in our F inverse notation. Another case. Now, this one is a fractional one with variables in the denominator. So we typically get the two-sided graph, okay? The plus 1 here, shifted this over, okay? And then the 3X also messes with it. Now, what is the domain? What values can this not be? Because we've got a fraction, a variable in the denominator, X cannot be -1. So let's go ahead and work this. We replace F of X with Y. We interchange the X's and Y's. We simplify, which takes a whole bunch of steps in this case. What did we do? We multiplied both sides by Y plus 1. On this side, they canceled, leaving me X times Y plus 1 equals 3Y. Okay. I distributed this X. Okay. Now, in this case, I took this XY to the other side, so I would have all of the Y's on the same side. I factored out the Y, leaving 3 minus X. Then I divided both sides by 3 minus X. This X by 3 minus X. That left me Y. Now, I replace with the F inverse notation. So here is my inverse function. Now we may or may not test this thing to see if it's correct, but that's how you did it. Well, here are the graphs of it. Okay, this graph and that graph, you can see, are reflected by this graph. This graph reflects this. That graph reflects the blue. And you see all of these reflect across that diagonal line. So yes, by looking at the graphs, we can say this is 1-to-1. Or we can do it by composition. And the composition gets rather nasty on this because of the compound fractions. Well, in this case, they're multiplying everything by 3 minus x, the common denominator, and it simplifies everything. This 3 minus x in the denominator cancels that 3 minus x, okay, leaving 3x. This 3 minus x cancels that, but we've got to have the 3 minus x here, okay? In other words, what they did and they did not show was they did the common denominator trick with this. Now, that simplifies to 3x over 3 equals x. The 3's cancel, and I get 1x. Now I got to try it the other way and see if it works. Again, we get the nasty terms. I wouldn't show this way. I would show multiplying x plus 1 times every term and then canceling. You're less likely to make an error that way, okay? Well, this still simplifies here, and here the 3's cancel, and we get 1x. So in this case, you're 1-to-1. What about this one? Now we're picking up an inequality. This is x cubed plus 3. Now, why are they saying for x is greater than or equal to 0? Well, what they're saying on this one, and I'm going to get out of here and put something in this again. Let me get back on the right page. They're only showing you half of this graph. Okay. And here, half of this graph. Now, if we look at this, uh-oh, what happened there? Something shifted. Looks good there. Huh, weird. Well, I'm just going to leave it right on this screen for the moment. This x is greater than 0. What that means is that they're only going to use half of this quadratic. If we use the whole quadratic, although it'll pass the vertical line test, it won't pass the horizontal line test. So they're doing what's called a restriction. They're restricting the values of x to only those positive ones. And if that's the case, this will now pass the horizontal line test. Likewise, if y is greater than or equal to 0, see the reflection of the x's and the y's here? Then they only take the part above, because if we use the whole thing, it wouldn't pass the vertical line test on the inverse, okay? we can still create the inverse, but the question is it 1-to-1? Now, here's the computations, okay? We replaced y's with x's. We isolate the y, that's a y squared right there. Funny looking 2. Then we take the square root of both sides and we get y equals plus or minus x minus 3. Okay, and then we replace the y with f inverse of x. If we've got this restriction that x is greater than or equal to 0 and y is greater than or equal to 0, then those pieces are 1-to-1. If we don't have that restriction, then they are not. Okay, now they're going to take the same problem and they're going to try to do the 2 compositions here and here. In this case, we get 1x. In this case, we also get 1x, okay? With the restriction that x is greater than or equal to 0. Now, I'm going to give you a moment to copy this down. Okay, now we've got another quadratic, x squared plus 1, but we put the restriction x is less than or equal to 0 this time. Okay, so y equals x squared minus 1. We replace n of x with y, or I could replace it with n. Okay, here. So now we interchange the x's and y's. We get the x's on one side, the y's on the other. To get rid of that square, we take the square root of both sides. And that in turn gives us y equals 1 minus x, or square plus or minus square root of 1 minus x. So that's our inverse. In this case, that's all that it asked us to do, was just simply find the equation of the inverse. So always read what the directions it is. They did not ask us to prove that it's 1-to-1 or not, although we could. Here's another one. Again, they're just asking us to find the equation of the inverse. So we replace g of x with y. We interchange the x's and y's. This time to solve it, we're going to square both sides because we want to get that y out from underneath the radical. So we square both sides. That gives us y plus 2 over here, and it gives us x squared over there. When you square both sides, you don't need the plus or minus. That's just when you take the square root or absolute value. Okay, now we want to isolate this y, so we take the 2 to the other side. So we've got negative x squared plus 2 equals y, okay? Or we take the x squared over here and the y over there, okay? And here's our equation. Now, I don't know if they'll have a problem like this one on the final this year or not, but they have had most years a problem very similar to this one on the final. They give you a graph. And by the way, this is usually the easiest problem on the final. All you have to do is graph its inverse. Okay? What's this point? This point is 1, 1, 2, 3, 4. 1, 4. Well, we take the point 4, 1. 1, 2, 3, 4, and up 1 right here, and we graph it there. In other words, we reverse the signs of all of these are reverse the X's and Y's, interchange the X's and Y's, the domains become the range of this. In other words, here were my X values that were the domain. In the inverse, the X values become the Y values. The range of the first one becomes the domain of the second one. And we graph the thing and it looks about like that. Okay? So that's all it is on this question. And that's how easy it is. Sometimes they put an equation that goes with this, but really all you got to do if it asks you to graph the inverse is just pick some points, interchange the X's and Y's, and graph those interchange values. Now, with that, that's the end of the objectives for today. But we've still got some time left. I'd like to go ahead and get started on the other. Well, no, we'll just go ahead and wrap up a little bit early today and stop with section 4.1. So with that, go have a slightly early lunch by 5 minutes.